Morning, everyone. Can everyone just confirm that you can hear us okay?
And seeing the screen also, please.
We're just going to give everyone a couple of minutes to get signed up here, and then we'll, signed in, and then we'll get started. We'll give people one more minute here, and then we'll get the presentation going. All right, we'll get started here. First off, just want to thank everybody for taking the time to join us for our first in many of our series of professional development hour presentations. Today we have Fikret from Armstrong presenting on the fundamentals of gas detection. He's an application engineer with Armstrong. Everyone who's attending the presentation today will receive a certificate for professional development hours that you can submit to your regulating body for either PEO or the ASAP program. It will also be recorded to view at a later date for later viewing as well on our website. So I will pass it over to Fikret to run the presentation today.
Thank you, Justin. I appreciate it. And hello and welcome, everyone. The good news is today is Friday. I know I am. I hope everybody else is in a good mood. I work for Armstrong Monitoring. I have just over 20 years of experience in the gas detection industry. Believe it or not, before I started to get into the gas detection industry, I thought that why would you need a gas detection system at all? I thought you just go to Home Depot, buy a carbon monoxide sensor and take it, put it in your house, and that's it. But after I got into the industry, I understood how important it is for the life and property safeties. And that became now the gas detection industry became one of the most important aspects of HVAC industry for controlling the ventilation system, etc. Without further ado, first of all, I'd like to thank our friends, if anybody from down south. I know it's going to be a long weekend for you for Memorial Day. For anybody from United States, happy Memorial Day. And today, my session's objective is to get us comfortable with the when, what, and why gas detection. Second, I like to develop an understanding of how to size a system and why we do it that way. Lastly, we wanted to understand which gas or gases or sensors to be used for different type of applications. There are a variety of applications that require certain sensors to detect or monitor target gases. What is your target gases? Obviously, that will be covered under the application section. I allocated the last 10 minutes for question and answer period. If you have any questions, please make a note of that and feel free to ask me. And at the very end, I will give you my email address as well as my phone number so that you can reach out to me at a later day if you have a specific question about the applications, about the gases, or even about the products that can be used for that. So we'll begin with that. My agenda is going to be why use a gas detection system, components of gas detection system, system design consideration when you are designing a system, what you need to be paying attention to, and then finally we talk about common applications. There are hundreds, if not thousands of applications out there, but there are some common ones such as underground parking applications or chiller room applications, battery charging room applications, etc. So we'll be talking about those and what type of gases that you need to be targeting. First, let's begin with why use a gas detection system at all. There are two main reasons, one of which is the life safety from the toxic and asphyxiant gases. Asphyxiant gases such as CO2 or noble gases that can deplete oxygen from the building envelope. Second is the asset management, asset protection from combustible gases. So you want to be protecting people as well, the property from explosion, from fire, from what caused by combustible gases. So these are the two main reasons that we really need a gas detection system, which is vital. A spin-off from that is, from these two, is the energy management. You will be controlling the ventilation system based on the gas concentration or the target gas concentration being leaked to the environment, and you wanted to detect that and start your ventilation system on demand. It is not that like old days, the fan used to be running 24 hours a day, regardless of the gas concentration. So that will reduces the amount of energy being used for the ventilation system. Lastly is the regulatory authorities. Regulatory authorities, we can equate a gas detection system or gas detection industry to fire safety industry. We all know in a fire safety environment in a building, you have to know how many sprinklers you put, what is the distance between each sprinkler, and you have to put your exit signs at certain locations. You have to have fire extinguisher in a certain locations. So these are all rules and regulation that was implemented long time. And for the past 30 years now, gas detection industry followed the same footstep. And there are some rules and regulation that a building designer, an engineering building designer, you have to comply with that regulation. The regulatory authorities, it all started with American Conference of Governmental Industrial Hygienists, or ACGIH. This is just a group, a volunteer group of professionals, medical professionals and scientists. They get together, they look at certain toxic gases, combustible gases, and other harmful gases that they may cause harm to an occupant of a building or harm people. So what they do, they pass on their recommendation to NIOSH. NIOSH is National Institute of Occupational Safety and Health. So this is just a recommendation. They pass it on to NIOSH, and NIOSH in terms advertises this or put this recommendation at the CDC, the Centers for Disease portal. And what is it that? It is something called a NIOSH Pocket Guide for chemical and other hazardous gases. they advertise it there, and I'll give you a sample of that pocket guide sample for a certain gas. What's entailed, what has in it, what useful information, and then later on, NIOS along with CDC they pass that on to OSHA Occupational Safety and Health Administration, along with other local authorities down south in states, in Canada, in provinces. Then they have their own rules and regulations, such as our own ASHRAE, and we have Canadian Center of Occupational Health and Safety. In British Columbia, WorkSafe BC is huge, as well as in California, Title 24. They have their own rules. For instance, we in California, instead of going for 50 radius, they go 40 radius and sensor coverage, and also the International Mechanical Code. Okay, so in a nutshell, ACGIH starts from all starts from there, and then they make their own recommendation down to NIOSH, and between NIOSH and OSHA and variety of local authority or local having jurisdiction, they can make that like a code, just like a fire alarm code. The engineers must follow that when they are giving or permitting the occupancy to a building. Now, what does the ACGIH provide? They provide the threshold limits values for time-way average. The time-way average is the average over normal 8 hour a day. So if you are working, let's say you are working in a place where you are repairing a car repair shop, how much of toxic gas in that case is going to be CO2 or CO and NO2, how much you are allowed to be exposed to it for 8 hours a day and 40 hours a week. Second, you have the STEL. STEL is short-term exposure limit, which is the maximum concentration to which a worker may be exposed to it. And then the last one is the ceiling, or TLV ceiling. This is the concentration that it is vital. So you must, during any part of the working for that. Now, the values that you see here, these are just taking as a guide. It is not an absolute. When I say it is a guide, meaning I give you an example. Here in Ontario, we set our CO alarm set points to 25 ppm of 25 ppm of CO as our low alarm. In some jurisdiction or in some states down south, they set it to 15 or to 10. Similar with other gases with NO2. So this is why the ACGIH along with OSHA, they make recommendation. They give you the guideline, and then from there, the local authorities, they put the codes together. They set their own values. If you look at this, is a you can download this pocket guide from NIOSH's website. Actually, it's about 500 pages and covers almost every toxic and combustible gases and other harmful gases. The information we will be looking for in that is the permissible level. For instance, the TWA, as you can see here, it is 35 ppm. For OSHA, permissible exposure limit is 50 ppm or 55 milligram cubic meter. And the other vital information you can get from that is your IDLH. IDLH is immediate danger for life health. So if you are exposed to that much ppm, which is 1200 ppm of CO, you must occupy the building immediately. This is vital. So this is it's a very important. Therefore, as a gas manufacturer, as gas detection system manufacturer, we set our high alarm level for CO at 100 ppm. In some jurisdictions, they go even more conservative. They go to 75 ppm. So imagine that at 100 ppm, we're giving you a high alarm. We start activating the fastest speed of the fan to purge the contaminant from the building envelope. We will never let it reach that high, okay? And the other good information that the pocketbook allows you is the CAS. The CAS stands for Chemical Abstract Services. For any gases, you can look at what's this gas is made of and what the properties of that specific gas. So when you have that number, the CSA number, the CAS number, you can look it up from the website, and you pull up the information about that. Okay, so for those of you interested, this is especially good for sales engineers whom they design a project. They wanted to know to have an educative conversation with the engineer or the project who put the project together, to have a conversation, say, hey, this is how we're going to set our alarm set points. Believe it or not, for past 20 plus years I've been working, I received mechanical drawings from engineers. They put most of the time I can see it. This is being cut and paste from somewhere. It says, you set your alarm set points for CO at 500 ppm. Well, no, you cannot set it to 500 ppm. So what I do, I pick up the phone, I talk to engineer, I said, I can set it up to 500 because the contractors will follow that blindly. Now it's up to me, up to you, that we can talk to engineer, we give them an educative discussion, say, no, this is, if you look at the NIOSH pocketbook, this is where we should be setting up our alarm set points, and this is why. So again, I'm giving you this information, and that's why we call it fundamentals of gas station or gas detection. This is something that we need to know about it before we even go further to dive deeper into the entire system. Okay. Now, what are the gases? Now we know why we need gas detection systems. We need them for life and safety of people. Second, property. Third is to minimize the wear and tear in ventilation system and to reduce or to save energy. And obviously the fourth one is a regulatory authority which they enforces that. But what are we looking for? What type of gases that we are looking for? That goes into certain categories. First, we look at the toxic gases. Toxic gases are typically measured in parts per million or parts per billion. And these gases, for example, are carbon monoxide, the silence killer, we all know about it. Nitrogen dioxide, believe it or not, nitrogen dioxide is much more toxic than carbon monoxide. I give you an example. The low alarm set points for carbon monoxide is 25. For nitrogen dioxide is 0.7 ppm, 0.7. It is deadly gas. And then we have ammonia. We all heard about ammonia gas leak in Fernie, British Columbia a few years ago. Unfortunately, 4 workers lost their lives because of the ammonia leak, massive ammonia leak in a hockey arena, I believe it was. And then you have chlorine and many other type of toxic gases. So toxic gases goes into the first category. Second is our combustible gases. Combustible gases are typically measured in percent LEL. LEL stands for lower explosion limit, and I'll be talking about it briefly soon. The gases are methane, propane, hydrogen, and many other type of combustible gases that are, if they leak and if they reach their LEL in terms of the concentration being leaked out, and you have a spark and oxygen, obviously, then you have an explosion. Okay. The other one is refrigerants. Refrigerants measured in ppm in general. Some of the refrigerant you see on the screen are absolute because of the Kyoto Protocol, because of the environmental impact. And quite frankly, the refrigerant, as you may all know, and you guys are in HVAC industry, the R value keeps changing. A new one being added, the older one being phased out because of the environmental impact. But my goal here is to show you that this is one of the gases falls into the same category that as a gas detection system designer or a manufacturer, we need to have sensors that can detect those gases. Okay, and again, it is measured in ppm, and also ammonia. Ammonia fits into the same category, refrigerant, as well as CO2. Now they started using, as you may aware of, the CO2 being used as a refrigerant. The fourth one is asphyxiant. Asphyxiant gases measured in percent volume. And that can cause oxygen depletion. You may have seen oxygen sensors in MRI room in MRI rooms where in hospitals. Why would they put oxygen sensors? Because the gases, the noble gases they use to cool down the MRI machine, because it gets very hot, very warm, so it cools down. When it does cool down there, because that noble gases, although they are not toxic, but if they leak out, they deplete oxygen in the environment very quickly. So in order not to harm workers in there and including the patients, we need to put an oxygen sensor in MRI rooms and in many other areas, in wineries, in cannabis grow applications or greenhouse applications, which we'll be talking about it later on. Okay, so asphyxiant gases and acetylene. Acetylene, you have one of them during the welding process, that you are mixing acetylene with other gases to melt metal. It can deplete oxygen, so it's very important. And a person being asphyxiated, it's immediate. It is not like you drowning. A drowning, you have a chance of survival. Being asphyxiated, it is like a light bulb being switched off. It's gone. And the lower, the in the atmosphere, for those of you not familiar, is 21% volume, or 21% volume oxygen level in the ambient. The rest is nitrogen. So if the oxygen level depletes or descends to 17.9, we are going to give you a low alarm immediately. And below that, it's high alarm, and you don't want to be there. Okay. The last one is total volatile organic compound. This is something that's becoming mandate that you provide sensors for it. So what is the total volatile organic compound? Any compound or any material, if you traces back to its origin made from fossil fuel, it can emit particles that can be harmful for human. Example, you put a new carpet in your house. You get that new carpet smell. That is organic material being leaked out of it. Many cleaning materials, cleaning bathroom and kitchen cleaning liquids, they all produce that. Paints, when you're painting your house. And this is why there's something called a new house syndrome. When you go to a brand new house is finished, if you spend an hour in that house, when you get out, you feel you have a headache or you feel tired. That is because the TVOC is being leaked out through that. Not only that, if you leave a house without any occupant, nobody in the house for 20, 25 years, you come back to it, you see the material in it, the carpet, the windows, the chairs, they start deteriorating, and that's because of that. Okay, so the TVOC is another category now. A lot of gas manufacturers, we started to produce monitors for it or detectors for it. Okay, so again, to recap, we know why we needed gas detection system in general, and we talked about the regulatory authorities, they enforce it, and there are some guidelines we have to follow, and also now we learned about the types of gases. These are the major ones that we can see them. Okay, now we put all that together. How does it work? Okay, now I know what I want. I need an oxygen sensor, for instance. This is my application. How does the whole system work in general? It all starts from your transmitter, okay, gas detector or transmitter. Gas detector, what they do, they designed to detect the concentration of the leaked gas. Which gas? A target gas, whichever your target gas is, CO, NO2, propane, methane, you name it. So the transmitter detects gas, and what it does, basically, it just sends out signal to a controller. Okay, now this signal that's being sent from the transmitter to the controller, it can be an analog signal, which is a 4 to 20 milliamp or 0 to 10 volt. I'm not trying to get too much technical here, but 4 to 20 milliamp. If it's 4 milliamp going out to the controller, control says I am okay, I am safe. 4 milliamp meaning 0 ppm of that target gas. If it is receiving 20 and anything in between, now the controller will take an action. Similarly, the signal being transferred, it can be a digital signal. A digital signal meaning that there is a protocol being used between the transmitter and the controller. And that digital signal, we typically call it a protocol. And that protocol in industry is a Modbus or BACnet. Highly likely you must have heard about BACnet and Modbus. But again, this is beyond the scope of this webinar. If anybody interested to understand how the communication happening and what is the difference between analog system versus a digital system, I will be more than happy to put a webinar session for you, even if it is one-on-one, so you can get more exposure to it. So now the controller receives that signal. It has its own, depending on the model, the complexity of the controller. It has a dry contact relays. Okay, it has a dry relay contact relays, or in some cases, it has a 0 to 10 or 4 to 20 milliamp outputs. Okay, so and once the controller receives that signal, and I'm a programmer here sitting programming this for a certain thing, and I'm going to start exhaust fans, supply fans, transfer fans, makeup air units, and even VFDs and motorized dampers, etc., which you are very, very familiar with it. And furthermore, I can turn on a strobe horn and strobe and horn to send alarm to supervisory office. One step further, I can send out a signal to outside world, to building management system, over a BACnet or Modbus or any other type of protocol that is being used. So again, in a nutshell, as you get this, the sensor transmitter detects gas, translates that into a signal, analog or digital, goes to the controller. Controller takes that command and implements or activates the sequence of operation that has been programmed in it by poor programmer. Then it does one of those. If there's a VFD, it starts VFD. If there's a makeup unit, it's going to start the makeup unit, etc. Okay. Now, I was asked a lot of time, you say your sensors cover 50, 50 feet radius. That's huge. How does it work? The way the sensor detects gas is on the diffusion method. Imagine we have a gas leak here. The source of the leak here, you have a high concentration. With the air movement, it's a natural physics thing that where the high concentration transfers over or goes over the lower concentration of the gas. So with the natural diffusion and air movement, before you know it, this reaches the sensor detects the gas and then sends signal to the controller and activates the alarm. Now, in some applications where you need to reduce that 50 feet radius, such as a chiller room application, You can, because or you're in a warehouse application where you have so many obstacles and shelves and all that, then you need to add more sensors in that location. And that comes to our, like when we receive a project in mechanical drawing, we look at the layout, we recommend it. But my point from this slide is, how does the sensor senses that gas? And equate that to somebody walking in a room wearing a heavy perfume, stands in the corner of the room. It doesn't take too long before the other person on the other side of the room can smell it. And that is where the diffusion from high concentration to the low concentration. Okay. The components of gas detection system, it's your sensor element. It starts from the sensor element. The sensor element being put inside a box, a unit with a circuit board and all that. The signal coming out of the sensor gets amplified in multiple levels so that the transmitter now takes that signal, translates it to an analog or digital signal, sends it to the controller. Controller takes care of the ventilation system and at the same time sends signal to the building automation system. Uh, Building automation system can start the ventilation also. In some cases, you don't need this if your building automation system is doing the job, the ventilation control. So you eliminate the monitor. Instead, the signal goes directly to the building automation system. Building automation system, or BAS, takes care of it. The sensor element, that's very important. There are 4 types in general we use: the electrochemical sensors, catalytic sensor, infrared sensors, and solid state sensors. To go to specifically talk about each one of those, it's beyond the scope of this course because it's going to take much longer time to discuss it. However, one thing to take away from this, infrared is the Cadillac version of the sensors. It's a lot of time used for, why? Because it's accurate and it takes much longer. It uses the light beam in detecting the particles, the leaked particles. Solid state sensors are much cheaper, for lack of a better word. The reason is because the technology being used in it, it's inexpensive to build, but the disadvantage, it can detect any gas. It really physically can detect any gas. So in order to get it specific to certain gas, you have to calibrate it for that target gas. And often that cannot be 100% accurate. And then you have a catalytic sensors. It's typically used for combustible gases. And then the electrochemicals are accurate also. They are used for toxic gases such as CO, NO2, and refrigerants, etc. How do you express the gas values? They are expressed in parts per million, or as I said, parts per billion, or percent volume. Now, a lot of people ask me this question. It says, what is the difference between ppm and percent volume? Any value between 1 ppm to 9,999 ppm, we say it's 500 ppm, 600 ppm, or 9,000 ppm, etc. But the moment you hit the 10,000 ppm mark, now it's becoming too much. So now each 10,000 ppm is equal to 1% volume. In other words, 1% volume is a 10,000 ppm. And this is typically used in when we are measuring CO2, for instance, in greenhouse application. You say, I need a sensor, it's 5% volume. 5% volume sensor equates to 50,000 ppm of CO2. But this is just an expression value, and you can also need to know when you are ordering your calibration gases, etc. The LEL and UEL, lower explosion limit and upper explosion limit, also typically used for flammable gases to detect the flammability rate for that gas. And this is a list of some gases showing you their lower flammability level. For instance, if you look at benzene here, if you look at benzene, it's 1.35. What does that mean? Meaning that if it reaches 1.35 in an ambient, and where is a spark and oxygen, kaboom, there's a fire. So this is something you need to pay attention to. And I can show you this in a graph. If you look at it here to the left side, okay, as you start, if the gas starts leaking, okay, from the premises. When that leaked gas reaches 20% LEL, I'm going to give you high alarm. We will never ever let it to reach 100% LEL. When it reaches 100% LEL and there's oxygen and spark, there is a fire. You cannot stop it. Therefore, we need to detect it where? We need to detect it before it reaches 100% LEL. And if you have, in some cases, when you have much more leaked gas and there isn't enough oxygen or spark, that's what we call it the upper explosion limit, where it is too rich to burn. And often you see this in ships, tankers, where they transfer combustible material overseas in the ocean. They put them all in a tanker and they literally seal it. So you have so much gas in there, but it will not explode because it's too rich to burn. Okay, and that is what fire tetrahedron, for those of you familiar with it, when you have fuel, oxygen, and source of ignition, you have fire. Okay. Now, once we have all that put together, now we'll begin with the transmitters. Transmitters, which you say, what does it do? It transmits signal to the controller, which it basically, it has a built-in sensor element. There's a miswording here. A lot of people say, I want to get a sensor. Well, the sensor is a sensor element which is inside the transmitter. A transmitter with the box and the circuit board and the sensor element all together becomes a transmitter that transmits signal to a controller. Okay, and the transmitters are available in variety. Like any gas manufacturer, a gas detection manufacturer can give you a signal out, 0 to 10 volt or 4 to 20 milliamp signal out, or digital communication over BACnet, and often they have a built-in relay contact. And now a lot of gas detection manufacturers aiming for wireless. It is not widely available right now, but it will be available as the technology progresses. When you have a wireless, obviously you will be eliminating the wires and conduits in that premises. The monitor, as I said earlier, monitor is the central, or they call it head end. In the industry, we use this terminology a lot. We call it head end. That's where the controller receives signal from a transmitter and then looks at its own sequence of operation programmed by a programmer. Then it executes a certain thing, such as strobe horn or dampers, transfer fans, exhaust fans, makeup air units, or even sending a signal to a fire department or fire panel. Okay. I'm approaching the 45-minute limit. That's why you notice I'm going a little bit faster, but I'm trying to cover as much as important information for the fundamentals. Designing gas detection system is important to know. Number one, this is important. Number one, you must understand the application. What is the application? Is it a car park application? Is it chiller room application? Is it battery charging application? Is this an Amazon facility, a UPS facility? What is it? Second, what is my target gas? What am I looking for? So once you have those two variables in the equation, it's very easy to recommend appropriate product. So you don't have to put a product in there which is overkill or underestimated. It's very important to understand the application first. Second, your target gas. Third, you specify a certain product. There are some considerations you need to take attention to as a sales engineer. How large is the facility in square footage? Okay, and how many sensing locations? Just like fire alarm code. Where do I put my sprinklers? How far apart they are? This is exactly the same thing. Is it classified area? Classified area where you need explosion-proof transmitters. Okay. Is there a fan schedule, sequence of operation? You need to ask the engineer, what's my sequence of operation? What do you want me to do when I detect leak gas. Often engineers don't know, so we have to provide that, and then later on they can change it. Is it standalone system, or it is connected to building management system? Is it in a wet environment? If it is, and like in a car dealership, you need to put a splash guard to the sensor to protect it from water splashes. Is there an exception of extreme temperature? We live in Ontario. In some areas in Ontario, it gets really cold. So we need to add a heating element into that, okay? Each sensor, what is the radius for each sensor, the coverage? The typical sensor in a perfect environment, it's a 40 to 50 feet radius coverage, as you can see here, okay, which that equates to 7,000 square feet. But that's not cut and dry. That doesn't apply on everything. In a chiller room application, you don't look at the mechanical room size. You look at the quantity, the number of chillers in the room. In a smaller room, if you have 2 chillers, you put 2 sensors. If your chiller is too large, I don't know exactly the tonnage of that chiller. Often you use 2 sensors. Why? Because the refrigerant gases are so heavy, it takes a lot of air movement to move it for the sensor to detect it, and therefore we put or we mount the refrigerant sensor near the leak source and also at maximum 12 inches above finished floor. Okay, but as a rule of thumb, in general, the sensor coverage is 40 to 50 radius, application dependent. And the mounting height, which I illustrated here, you look at the air density. If it is heavier than air, obviously it goes to 12 to 16 inches floor above finished floor. Same or close to the air density, then you will be mounting at 5 to 6 inch, and much lighter like hydrogen, methane, it can be mounted near the ceiling. The location important. Keep sensors away from area with stronger than airflow. I have seen a lot of time, especially in Ontario. I was called for a city where they repair trucks. They mounted the sensor near the gate, the overhead gate. Each time when the gate opens up and closes, especially winter time, the air comes in, rushes in, it puts the system into alarm. So it's very important where you mounting your sensor, avoiding in areas where there's no natural air movement. You need, because as I said a few minutes ago, the only way the air gets from the high concentration area to the low is by diffusion. So you don't want to abstract that. Ensure sensors are easily calibrated for a technician to go there to do a calibration or replace it or do a maintenance on it. And also mount sensors away from areas where vehicles may potentially impact it. A perfect example for this, at Peel region here in Toronto area, I was called for a recycling facility where they bring in the recycled material, garbage, they dump it there, and then they have this huge Caterpillar machinery. They lift all the garbage, and as they go back and forth, they hit the wall where the sensor is mounted and they break it. For that, I need to know about it. If so, I'm going to provide you the metal guard with the sensor so you can protect it. So again, designing a system, putting a gas detection system together, there are so many factors involved in it. We started from your target gas. We started, your application, what it is. You need to know how far apart those sensors need to be mounted, how high I'm going to be mounting them. Not only that, what type of sensor if I'm using. If an engineer comes to me and says, I want a solid state sensor for a refrigerant application, I would say, no, you're not going to get an accurate reading, because our main purpose from gas detection system is to protect people and protect properties. That was my first 2 things at the very beginning of the webinar. If you're telling me, you want to put a solid state sensor where a place you're not going to get an accurate reading, I will do that, but it's your responsibility. In this images here, I'm showing you, it's a perfect example where you mount your sensor to have a perfect coverage. So in the image in the left, With 2 sensors mounted right in the center of the room, I can cover the entire area, or almost. But if you are limiting it, you're mounting the sensors to the wall of the premises, now you need more to cover. And this often happens in a car repair shops, where in the middle where you have, they put all the lifts where they lift the car up and down. There is no column in between, inside or in the center of the room. So we are forced to put the sensors on the walls of premises, and that dictates how many sensors you need to put. So here again, the 50 feet radius does not apply, because I cannot cover everything. And often we use this application or use this method when we design. When I design a project, I put my circles and I'll make sure that I'm covering everything. If the mechanical drawing tells me you put 10 in there, when I do my coverage, I know by 10 I'm not giving you an adequate coverage. I will increase or sometimes decrease the number of the sensors. Okay, so I put this image in there, just give you an idea about where I can mount my sensors and how that affects in terms of the coverage. Common applications, there are so many of them. Here I highlighted just a few: car park, ice rinks, warehouse, wineries, weldings, etc. So for vehicle exhaust, this is a bread of butter of the gas detection industry up until now. At least it's a parking and maintenance facilities, dealerships, fire halls, ambulance bays, arenas, etc. Commercial refrigerations, toxic gases, wastewater labs, etc. So if you look at individually at each one of those applications for the next 5 minutes, for car park applications, we have CO, NO2, and propane. In some provinces, like in BC, they are still using propane gas for underground parking. And here it gives you a typical layout for underground parking, where we allocate our sensors depending on the size of the area, which I just said where I should be locating my sensors, and then I give them a system. In the system, you got several sensors connected to a controller, and controller typically mounted somewhere here, and in a mechanical room to activate fans and all that. In a chiller room application, ammonia, refrigerant, carbon dioxide are being used also. One thing is important, I put on the screen for chiller room application, ASHRAE 15 and CSAB 52 code, which in here it says alarm can only be acknowledged from inside the mechanical room. I put a quick diagram for you here. You have a controller. You notice I said each chiller will take a sensor regardless of the size of the room, and you put one strobe horn in and one strobe horn out. But you pay attention, the strobe out does not have a stop push button. The stop push button is only in the one inside. Why? To comply with B52 code, CSA B52 code. So somebody accidentally will not go outside, shut off the alarm, and then you harm people inside. Furthermore, if your mechanical room has more than one entrance, you put a strobe horn at each entrance in the mechanical room. So these are things you need to pay attention to it when you are designing a chiller room detection. Swimming pool, you get all that thing in the water, as you can see. The target gases: chlorine, carbon dioxide, and ozone. For brewery, CO2 and ozone. Why do we put CO2 in there, and why do we put ozone? Mainly used for cleaning. Now, were you putting a CO2 in? Often if there's a larger tanks of CO2, then you will need to put an oxygen sensor in there, because CO2 depletes oxygen. So we need to protect people from asphyxiant gas. Lastly is my battery charging station. Battery charging station where as you can see here in warehouse UPS facilities and other facilities where you have a battery operated forklifts. When you're charging them, you need to detect leaked hydrogen from the overcharging a battery. Okay, so there are So there are many other applications that are, the list goes on and on. As I said, if you are interested to get to know more of this, you feel free to contact me and I will go over this in much detail. So I think I am right on time, Justin, for
Yeah,
taking
that's perfect.
questions and answers. Please go ahead. Okay, I don't hear anybody asking question or maybe writing something. I don't know if Sarah or Justin, you're seeing it because I don't.
Yeah, nothing on my end here.
Okay.
Well, like Thegret said, if there are any questions that come up after the fact here, feel free to reach out to your to Thegret directly, or you can contact your local Odell office. We'd be more than happy to assist you guys with any questions about design or product related items. So
Yes, that's my email address and that's my direct line with extension. Please feel free to reach out and or any other associates with Justin's team. Between both of us, we can get you the answer. There is no question. I know a lot of people times say, it's a stupid question. There isn't a stupid question. Why I always say that? Because the gas detection, it is not something taught at the colleges and universities. You can go get your doctorate degrees in mechanical engineering, in architecture or in electrical engineering. There isn't a school that you can go learn a gas detection. I personally, when I was introduced to it, I am by definition electronics. I took electronics engineering back when. Uh, and then I was exposed to gas detection. For me, it was, as I said at the very beginning of the webinar, I said I thought this was just something simple. You go by Home Depot, buy a CO detector, but it is not. As you can see, after I went through the fundamentals of it briefly, it is not something that that can be learned easily. It takes time, and that's why we are here to help.
we did have a question about the recording for the webinar. So all the recordings will be on the Odell HVAC website, and we will send out the link to that location on our website to look at all of our past webinars for future viewing.
Now, before I say goodbye, I like, as I always do with my all webinars, I mean, if you have any comments about what you heard, and I hope that we met your expectation. If you have a comment, please let us know. Something we can improve it for a later sessions. I am more than happy to listen to it. I take the criticism very well. If you don't take criticism, you will never succeed on what you do. So a simplest comment, a simplest note, I am more than happy to hear it. If you can send me an email or call me, we can talk about it, or talk to Justin about it. It's okay. And thank you very much all.
Yeah, we'll log off for the day, and yeah, thank you again everybody for coming, and enjoy the rest of your day and the weekend.
Thank you guys. Have a great weekend.
Yeah.
Bye-bye.